Hello class, in this video I'll be showing you how to find all second order partial derivatives of a function when the derivatives require the quotient rule. Let's begin. Okay, so I've already gone ahead and found both of the first order partial derivatives. The one with respect to x I'll highlight in pink, and the one with respect to y I will highlight in green. I've also gone ahead and labeled both of the numerators f and both of the denominators g. So I'm going to start by finding both of the second order partial derivatives of the function on the left. So I want to find the second order partial derivative with respect to x. So that means all terms with a y in it are either going to be a constant or a coefficient. So starting with the numerator, negative 5y is going to be a constant. So I write that in pink. The denominator is x plus y squared. Now, we want to take the derivative of each of these two expressions with respect to x. So for the numerator, the partial derivative with respect to x is going to be 0. For the denominator, the partial derivative with respect to x is going to be the following. It's going to require the chain rule. So I'll first apply the power rule, and then I'll take the derivative of the inside function, which is going to be 1 plus 0. So this cleans up as 2 times the quantity x plus y. So now we are ready to apply the quotient rule. So we want the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And that's all divided by the denominator squared. Okay, so notice that the expression here, or the term on the left, that term is going to equal 0. Also notice that raising the 2 to the 2 power is going to create a 4 in the exponent. So this will reduce to the following. Which will equal and there is the first of 4 second order partial derivatives. Okay, so now I'm going to shrink this a little bit to give me some room for the next one. Okay, now we are looking for the second order partial derivative with respect to y. So now every expression or every term or every factor with an x in it is going to be a constant or a coefficient. So the numerator isn't going to change. It's still negative 5y. And the denominator is not going to change either. But this time, x is going to be the constant because we're taking the partial derivative with respect to y. Okay, so now we're ready to take the partial derivatives of each expression. So the partial derivative with respect to y of the numerator is going to be negative 5. The partial derivative with respect to y of the denominator is going to require the chain rule. So I will apply the power rule to the original expression, then multiply by the derivative of the inside. So that is the expression 2 times the quantity x plus y. And so now we can write out the next partial, or the next second order partial derivative. Okay, so that is the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And since there's already a squared term in the denominator, squaring the squared term will lead to a fourth power. All right, so let's take a look here. Every single term has a factor of x plus y. So what I'm going to do is I'm going to factor out one factor of x plus y. And so that will result in that factor canceling. We'll have one less factor in the term on the left, and we'll have one less factor in the denominator. And after everything is all simplified, here's the result. Okay, so that is the second of 4 second order partial derivatives. Moving on. So now we will work with the first order partial derivative with respect to y. And we want to take the second order partial derivative with respect to x. So the numerator and the denominator are going to be a little bit different this time. So in the numerator, 5 is the coefficient of x. So we're taking the second order partial derivative with respect to x. So x is the variable and y is the constant. Okay, so for the numerator, or sorry, the denominator, this is x plus y, and in this case y is a constant, squared. Okay. Now to take the partial derivative with respect to x of the numerator, and that is going to be 5. And taking the partial derivative with respect to x of the denominator, that's going to be 2 times the quantity x plus y. So here is the third second order partial derivative. It will be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. And again, since the denominator is already squared, when you raise the second power to the second power, you multiply the exponents and you get a 4. All right, now you may have noticed that every one of these terms has a factor of x plus y. So I'm going to factor out one factor of x plus y from each term. So there's no more factor of x plus y in that term. We will remove one factor of y from the term on the left and in the denominator. Sorry, that's supposed to be a yx. All right, so when I write down this second order partial derivative, it may look familiar. Where have you seen this before? Where have you seen this before? All right. For the last one, we want the second order partial derivative with respect to y, which means every variable that is a y is going to be a variable, and every x is going to be a constant. So for the numerator, 5x is going to be the constant. And in the denominator, the x is going to be the constant, the y is going to be the variable, and we're going to raise that to the second power. And now we are ready to take the partial derivative with respect to y of the numerator, and that is going to be 0, because 5x is a constant. And the derivative with respect to y of the denominator is going to be 2x plus y. And we're now ready to put together our last second order partial derivative. So that's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. All right, so this term that I'm highlighting in yellow, that is going to be 0. So what we're left with is this. Which reduces to this. And that is all for second order partial derivatives.